wassalamu ala rasulullah wa ala alihi wa sahbihi ajma'in. We are welcome to the class today. So inshallah, we continue from the review of some of the concepts that we covered earlier, inshallah, after which we hope to move on to the next topics, bismillah. So last week, we did discuss some of the various ways of dividing our data. And I remember we stopped and one of our doctors asked a question regarding tenfold cross-validation, and that was how we ended that day. Now, so the next we were going to pick was describing classifier errors. So as we know, we were talking about supervised learning, which is divided into classification and regression. So when you want to describe classifier error, majorly we have the one that is most popular is the binary classifier. So when you have your classes are only 2 in number. So we've had videos that describe this extensively, both the binary and the non-binary and what of the options you have. So but for binary, most importantly, thank you. Yeah, so when we say true positive, so this is in binary classifiers or classification problem, you are positive or negative. So positive is okay, this is what we're looking for. We want to see if somebody is diabetes or not. So true positives, we represent those cases that the original value is positive, and our algorithm also predicted the outcome to be positive. So we call it true positive. That is, the prediction of that positivity is correct. That is true positive. But when we have false positive, it means the original answer is negative, but our prediction, our model is predicting it to be positive. We say, okay, this prediction we are having is false, called false positive. And then we have the true negative. It means the original answer is negative, and the prediction is negative. So we're gonna call it true negative. So, and then we have the false negative, whereby the correct answer is true, but then our system predicts it to be false. So we call it false negative. And false negative varies from different application areas. If we are in medical area, false negative is a no. We don't want it because that is saying that somebody who is sick, you are saying that he is not sick. For example, we develop a machine learning to do early screening for diabetes. So we don't want it to miss people who are already having this disease by saying, oh, you are okay, you are good. And this person might go home, continue with normal lifestyle, and then it could get complicated outcome of diabetes. So that is why false negative could be very, very serious in medical. However, when you take it to other application area like industry might want to have false negative, which means, is my product okay to be sent to the customer? Machine learning says, no, it's not okay, even though it is okay, but it says it is not okay. So it means you have to do another quality check on the product before you send it to the customer. This is a better mistake for the industry. They can double check. However, false positive is a no for the industry. Because if something is not good and the system reported it to be good, in that case, you will not double check the client's package before you send it out. So the client will receive a faulty package, which is very bad for the industry. But for medical, we don't want false positive, but then if you have false positive, it is still okay. It's not as serious as false negative because you are diagnosing somebody to have diabetes, meanwhile the person doesn't have diabetes. So you will go to the clinic for further checkup, and during the further checkup, then they can detect that, oh, this person is not having a diabetes. So this is called false positive. So for medicine, false positive, false negative, they are both mistakes. I hope you get me right. We don't want it. We don't want any of them. However, if you are to choose between the two of them, then we go for lesser evil. So in which case that we don't want this guy at all for medicine. False negative is dangerous because people will continue to live normally thinking they are okay, meanwhile they're already killing themselves silently or gradually. So if you have a model, you build a new model, and that model is doing very fine, you got 98% accuracy. Another one is getting 97% accuracy. But the mistake from this guy, which is 98%, all the 2%, they are coming from these, false negative. But for this one, the mistakes are coming from these. Then we will go for these for the final deployment. We will go for this 97%. Why? Because it is a medical application, and false positive is a little bit manageable mistake. But false negative, even though it's having 98% accuracy, but the errors are more costly. This one is making costlier error compared to this one. So sometimes when you develop model, this is called discrete discussion of your result. So that is why it's not just enough sometimes to just conclude that, okay, my model is getting 98%, so I'm better than 87% that was developed before. It's not enough. I want to see the mistake from this old one. Maybe their mistakes are all false positive, and your mistake, they are all false negative. You thought you have produced better result, but this is not good for medicine. If it is an application in medical area, it is not good. Although you are celebrating 98% over 97, there's no need to celebrate, because the mistake you are making compared to the mistake of this guy, your mistake is more than the mistake of this lower percentage. However, if we take it to the industry now, like SABIC, then it will be the opposite now. So if the mistakes are false negative, this one are false positive, SABIC they can manage false negative because it will make them to double check the product before they send it out. So that is why you can see it depends on the area of application you are treating. But our target is to get 100% for these two, so that our classification is going to be Mia Filimia, 100%. But we know in real life, you might not be able to achieve your target. So that is why we discussed the implication of this. Now, then we have other measures like recall, precision, F measure. Once you got these 4 values, from there you can calculate every other value. And then depending on the area of application, there are areas whereby the precision, the recall, the F measure, which we've discussed, and we're going to also mention them in more detail as we proceed. Because what we use to produce this is what we call confusion matrix. This is the accuracy. Accuracy is true positive plus true negative divided by total number, all the 4. True positive, true negative, false positive, false negative. So what's the total number that's correct? Reclassify. Now, all this we call confusion matrix. Confusion matrix is going to be taken later as a whole topic. So, because matrix, as the name implies, you can see confusion. So sometimes it confuses people. So even experts in this field sometimes still find it difficult to answer direct question from confusion matrix. And it's very, very important. You don't just get the percentage of classification and go away. No, you have to go inside the confusion matrix and analyze your result. So am I doing fine or I'm not doing fine? So you can see here, this is the actual, this is the true value, and this is the predicted value. This is the output from the machine, from the model. So the actual value here is positive. So our model predicts positive. That's why we call it true positive. But here we are predicting negative by our model, but the original answer is positive. So we call it false negative. So my prediction is false. It's not correct. That's the meaning of false negative. But here the original is supposed to be negative. We predicted it to be positive. So we call it false positive. Positive prediction that is not correct. But here our prediction is negative and the correct answer also is supposed to be negative. So we call it true negative. And this is how confusion matrices are produced. So you can see this kind of example now. So you can say, okay, this is the predicted class. This is the hypothesis function after we train our model, H or Y. Then this is the actual class that is given. This is the given value. So this is by, this is positive. By is positive. By is positive. No by is negative. So take note of that. So now you can see here that the given value is positive. Our prediction is positive. So there's no error here. There's no error. So we're going to count. We have false positive. We have false negative. We have true positive. Then we have true negative. So we have to count as we proceed. So let's say I have the prediction is by and the actual is by. So this is no. So which number, where do I put this value? There's a 1 now for any of these 4. Which one do we put 1 plus now? Which one get plus 1 now? Because we are counting how many false positive, how many false negative we have.
True positive.
No?
True positive. True positive.
Thank you very much. With this one, we are having true positive. Excellent. So our actual class is by, but our prediction is don't buy. So there's a mistake here. So which kind of mistake is this?
False positive. False positive.
Let's look at it once again.
False
The original one is positive. This is what we are given. But our prediction actually is negative as we define here. So we predicted to be negative. So what do we say this?
False positive.
Negative. False negative.
Negative. False negative. Thank you very much for the attempt. We're going to decide based on our prediction, not based on this guy. This guy is given. This is the outcome of our model. It's our model that will determine whether it's false positive or false negative based on what is here. So because this guy is predicting negative, he's saying that don't buy something, which is negative prediction. We now compare it with the actual. The actual actually is positive. So our result is saying my result is no negative. So it's because it's not the same as the actually given, we say it is false negative. So the negative prediction you are giving me is not correct. That's why we call it false negative. That is, you are a liar. He lied that it is negative. Now, let's move. Do we all agree on this?
Yes.
Okay. So I take time because, like I said, confusion matrix itself could be confusing. That's why it's a thing to pay special attention to when you do the actual model. Now look at buy. This is positive. This is our prediction, buy. But the actual is don't buy. So what is going to be this?
False positive.
False positive. Thank you very much. Because the prediction is buy, but the actual value that's supposed to be the correct answer is don't buy, which is negative. So it is false positive. The positive prediction that is not correct. This one is buy. I think this is clear to everybody now. This is true positive. So don't buy. The original result is also don't buy. So this is what? True negative. That is negative is the answer. Our prediction is also negative. So our negativity prediction is correct. True negative. Don't buy. The original one is buy. So what do we call this earlier? False what? False negative. This is the one that will determine for us. I hope we are not confused. This is the guy that will determine is false negative. Because our prediction is negative, but then the answer is positive. So we say your prediction is false negative. For this one, no buy. That is true negative.
Negative.
Yeah, true negative. Thank you. Buy. This is true positive. And then buy again, true positive. Don't buy, true negative. Thank you very much. So you're gonna count it. It is true negative. 1, 2, 3. That is 3. True negative is 3. True positive 1, 2, 3, 4. So true positive is 4. And then we have our friend false negative. Do we have any? 1, 2. That is 2. And then false positive. Any guy there? False positive 1. That's only 1. So what's the total? 4 plus 3, 7, 10. This is why you know maybe you are correct or you are missing something. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. See, if you fit it in here, it's a way for you to cross-check. The total sum from this side to this side and the total sum here, when you add them, they must be the same thing. Total for this side and this side that is here, when you add them, they must be the same thing. This is how you cross-check that, oh, I have not mistakenly called false negative, take it to true negative, or the other way around. So once we know this now, we know that, okay, our total classification accuracy is going to be 4 plus 3 divided by 4 plus 3 plus 2 plus 1, which is going to be 7 over 10. That's going to be like 70% accuracy. That is our accuracy. And the other formula also can be applied accordingly. So this is how we evaluate classification problem. Now, I hope that is clear. So before we move on, now. Okay. Now, before we move to the regression, I would like to briefly, as part of our revision class. Now, I'm going to switch a little bit so something that we have done in the weaker environment. Okay. Now. Yeah. Can you see my screen?
Yes.
Okay. This is weaker, which we recommended for us if you have taken the pain. Try to, if you didn't install it yet, try to install it. There are so many options. You go to the Explorer. So we click the Explorer, which is the weaker. So this Explorer, we open for us. We are getting ready to load our data. Everything is gray out. You cannot do anything now. The only thing you can do is to open the file. We call it pre-process. So you go here, open your file. So when you want to open your file, you go to the location of your data. You go to the location of your data, and then you open the data you want to. Your data can be in .arff. This is the standard data for Weka, but at the same time, it allows you to put it in CSV. You can put it in CSV. It can also be in .data format from there. This is from MATLAB. And so many other format, but CSV is common. This is just convert your Excel file to CSV. Now, so I'm going to load my initial data. I go to my library here. This is local disk. Local disk. This is its program file. Program file. Then you're going to have Weka. There's Weka there. So there's data. There are sample data from Weka. So I want to work on diabetes. So we are opening, we are loading diabetes data. Now, this is the data. The moment you load the data, you can see here that you cannot carry out classification, clustering, and other activities. So these are the inputs. These are the inputs. You can select of them. You can see, you can visualize them. The case may be. But this is the class that you want to predict. So we have 500. So those people that tested negative, they are 500. Those that are tested positive, they are 268. So this is called imbalanced data. We'll discuss those more later on, which is normal in our population. We want more people to be healthy. We don't want majority to be sick. So this is normal population. So majority are negative, which is good. So this is the target. Usually when you prepare your Excel file, this class should be the one on the rightmost side. In that case, automatically it will be the last one here, and weaker will automatically pick it as the output. However, if you put your class in any part of the file, then before you run your program, you have to select which of these attributes is the target. So in order to avoid you forgetting, I usually recommend that you make sure that your data is on the rightmost side of your Excel file or CSV file. Now we go to classifier. Now. You can see here, this is what I was saying. You have to select the class, which is the class you want to predict. If I want to predict age, I'll select age as my class. But because it is already here, so I say, okay, this is my class. Automatically, Weka selected it because I put it at the last column of the data file. Now, you can see here, this is what we discussed last week. One of the stuff we reminded ourselves, and Dr. Abdulsalam asked a question on cross-validation. This is cross-validation. You can change that 10 to be 5-fold. I don't want to have 5-fold. I want to have just 5-fold. But the majority, based on the experiment, they recommended to use 10-fold cross-validation. Then we have our friend here called the percentage split. So you can, if you don't want to use this, you use this. So I want the default is 66. I want it to be 70% for training and 30% for testing. So, and there are more options you want. There are several options you want. The output, you want the output to be out. You want to see the prediction output. So many other things you can play with here. But let's say, okay, we have loaded our data. Here you choose your algorithm. So we want to use the lazy classifier, our friend, which is IBK, the nearest neighbor. Show me your friend. I will tell you the kind of person you are. So we selected IBK. And then we are training with percentage split. We don't want to use cross-validation. Okay. So here we go. So it's done. It gives me, this is the correctly classified instances. 169 were correctly classified. Mistakes were 61. Mistakes, they have the false negative and the false positive. These are the mistakes. While the correct one, they are the true positive and the true negative. So this is 73% of the data, and the mistake is 26%, 26.5. And there are other measures we discussed later, ROC and host of others. And this is our confusion matrix, the one I was talking not before. This is the number of healthy people classified as healthy. This number of people not healthy classified as not healthy. You see? And then it continues like that. You can see these are the correct classification. With these are the mistake. Usually the mistake is on the left diagonal. Oh, I'm correct. Left diagonal, that is, this 29 is one mistake, this one is another mistake. Now, how do we get these numbers out? Where is my actual prediction? I want to check it myself. You can do it. It's not showing for us now the actual predicted value. Because you can actually decide how these values are done. So I can go back here, more options, and I can try to manipulate and say, okay, show me the result. Output prediction, null. So I will now choose, okay, show me the result. Show it for me in plain text. I want to see it in plain text. See, display it for me. So I want to see the actual prediction, how it was done. So I have to run the experiment again. And then you can see here. This is the result. You see, this is the actual prediction. This is the output. The actual and then the output. This is tested negative, predicted as tested negative. Tested positive, predicted and tested negative. And then the error keep growing to be calculating the error to the end of the class. That is showing you, okay, the actual, you know that, okay, this is number item number 230. The original was tested negative, but predicted to be tested negative also, which is correct prediction. So this is an example of how, if you don't want to use percentage split, so I go back to and then I run. So we have This time around, a little bit of difference in the error. This is 70%, then 29%. So, and then we have the confusion matrix, totally different. Because now we're using cross-validation. That is why it's very important we have to document everything we use. The moment you see anybody that reported an outcome from machine learning and did not specify the kind of data partition used, that is, it should be disregarded. That you shouldn't reckon with such a paper if it is, no matter where it is published, because such paper cannot be reproduced. So the condition for you, you must mention how you divided your data into training and testing set. And then this is the first method we use, the second method, cross-validation, which we explained. And then there's another option that, okay, I divided my data into Excel file by myself. So I have the training, I use the training set separately, and later I will provide the testing set. That's also fine. That's another option. But then that one will waste a lot of your time because every time you have to be clicking it to upload, to load the file. You have to open the file for the test. But then if you remember, last week I mentioned that there's an option to divide your data into 3 places: training set, validation set, and the final testing set. If you want to use that option, then you go for percentage split first. See, you go for percentage split where you are going to have 70% for training. See, and then once you do the training and testing, because this only do training and testing, then the one you have kept separately now, then you are going to upload it using supply test set. So we bring the third one in from here. And if you like, you can also use these 3 times. Give us the training set separately, give us the testing set, that is the validation, then give us another testing set, that will be the final testing set. So this is why it's so simple. It's a very, very easy to use graphical user interface-based machine learning environment that I usually recommend for people that's just starting machine learning. As you move on, then you can move into other, like using Python and so many other stuff that I've explained last week. That programming is different from machine learning. So when you start learning machine learning with programming, so you'll be learning programming at the same time learning machine learning, and bring down a lot of opportunities. It slows down the learning process, and along the way, you can get stuck in the coding for several days. So that is why I usually try to separate learning machine learning from learning programming. There are 2 different concepts. One does not affect the other. But once you are very much comfortable with machine learning, you know the operation, you know how you know the procedures very well, then you can go practice it in any environment you might want. So that is introducing us to the brief things we have covered in our introduction, because we're going to make it as practical as possible. So you load your data. Once you load the data, then do the classifier, choose the classification algorithm you want. There are so many of them. You have the meta, which we are going to start with soon. You have the function, SVM, multilinear perceptron, that is neural network, and a host of other methods that you can choose from. Thank you. Any question on this? I go back to the slides now. Okay. So now, I hope you can see my slides.
Yes.
Okay, thank you. Yeah. So now, since we say supervised learning is made up of regression, that is prediction of actual values, we talk about it's made up of regression and classification. So we talk about classification, and this is regression. Here you want to predict actual value. You want to predict how long will a patient live before he dies. Maybe a patient has just been diagnosed with a particular disease. There's a way you want to do some estimation based on previous history. The first thing is we could have multi-level predictive solutions. The first thing is to predict, is this patient going to survive or not? That is going to be a classification problem. Is he going to survive or is not going to survive? So based on historical data that we have, we can predict. You see? So that if we say this patient is not likely going to survive, then we can pay more attention to the patient to prevent that prediction from coming around. It's not for you to neglect the patient. We should use machine learning positively. You see? So when machine learning predict that somebody might die, it is for you, the medical team, to give him or her the best possible treatment so that you can avert it. Not that okay, just abandon it. No. Just pay attention to that. Now, whatever comes out of machine learning is not the absolute truth. We only make it easy for us to know where to focus our attention. For example, in one of the recent research that was done on COVID-19, it was realized that the result outcome raised a lot of questions, but then the participant had to justify that, look, what really happened is this. Because they noticed that in the comorbidity, people believe that people with diabetes and obesity, they are more likely going to die of COVID-19 because of their present situation. But that particular result of the experiment, and research, shows that majority of the people with diabetes didn't die. What was responsible? They now realize that in that particular area where they gathered the data, people are already apprehensive that people with diabetes are likely going to die of COVID-19. So whenever anybody is admitted with diabetes or that are diabetes already, they pay more attention to them. They give them the maximum possible treatment, take them to ICU. By so doing, because of this extreme care, they ended up surviving. Unfortunately, compared to other people that they thought that, oh, this guy has no diabetes, it's okay, it's not obese, just keep him in the normal ward, it's gonna be fine. Unfortunately, it was not fine. This thing happened, this is because we are human. So what I'm saying in essence is the prediction outcome should not be taken as, okay, this machine learning has predicted that somebody is going to die, let us just abandon the patient. No, it is for you to do more effort to prevent this particular prediction from coming to reality. So once you predict, okay, a patient might die, then you move to the next stage. We want to estimate how long will this patient live before he or she die. And that will take us to what we call regression. That one is no more yes or no. It is now a problem.
Assalamu alaikum.
Alaikum salam.
Yeah. Thank you, Professor Adam. I'm very sorry for taking you back. I just want to get to the point quickly.
Okay.
When you talk about dividing the data, so and you want to do cross validation,
now
that you have to keep the data separately. So let's say, for instance, I have a data of like 100 points. So does it mean I can divide the data, for instance, to like, okay, let me say like 70 for training, then 20 for testing, and the remaining 10 for cross validation?
Yeah. Thank you very much, Doctor. Excuse me, I just opened this. Okay. Yeah. How we can see my weaker screen?
Yes.
Okay. Yeah. Yeah, the question is, you can do the division in two ways. Yeah, you are correct. You divide the data, though this data, your data is a little bit small, so this kind of data, usually we recommend cross-validation for that data. Anything 100, 200, they are considered very small because machine learning need to see a lot of data to be able to produce models. Yeah, but 100 is really very small. Even dividing it into two, some people consider it very small. That's why they go for cross-validation, which means you use all the data as training set in stages. So, but however, we have some reviewer that will insist that you must use 3, or like you just said, it's okay. Divide the data into, you can do it manually by yourself, divide it into maybe 70% for training, 20%, 10%, 15% for validation, and then another 15% for final testing. So if you want to do that, you can use the first one, you load this one in Use this one to load the 70%, which you have broken it down in your own file. Once you're done, supply the testing set, which is the first validation set, the 15%. Bring it in, get some results for it. Now you carry out another one for this. We are going to do this 2 times. Then you load the one for the final testing set. This is one option of doing it. Another option is to use percentage split, but this time you have to be careful because you're going to use calculation. What do? You remove the last testing set from your data, which is the 15% now. Out of 100, you remove 15 samples, remove it from the Excel file, and now bring the complete set into one. That means you are going to have 85 data samples. Am I right? 85 data samples. You put it in one CSV file. Now, when you data, what is, if you want to, out of, a mathematician can help us out of 85 data sample, what is 70% of that 85 now? I hope you understand the mathematics we are trying to do. We want to remove 15 for testing. Out of 85, but now this is the full data now. You have to calculate the percentage correctly because now the full data now is 85. 15 minus 85, so 15 minus 85, what's going to be the percentage? 15 out of 85.
That be 70 or what?
15 out of 15 divided by 85 times 100. That's going to be 17.6%. 17.6% minus 100. So you're going to have 82.3. Here you're going to have 82, let's say 0.5 or 82% for training. You see, 82% for training. So it will automatically use the remaining 18% for testing. Then the third one, you have to go and supply the third one here. This is another way to go around it. I hope that is clear, Doctor.
Yes, yes.
So this is how we work with that division of the stuff. So now.
Thank you very much.
Yeah, you're welcome. So now the regression, we're talking about the regression, that here you predict the actual values. So when we can see a sample, you want to predict the price of a car. Usually when you want to sell your car anywhere in the world, you want to predict what's going to be likely be the value of my car. I want to know before I start advertising it. So you can decide to have car attributes, then the price, then you generate the model that will do the prediction for you. So for the regression, we have several ways of doing this. That means absolute error, mean square error, means absolute percentage error, means percentage error, root mean square error, coefficient of determination, and so many other evaluation measures that you can use to ensure that you are getting the right thing or you are not getting the right thing. So that is on regression problem. So regression is mostly the engineering, both can be from both engineering or medical or any other area of application. Usually when I want to do regression, classification, sometimes they can coexist together. In which case you start with classification, like the sample I gave. Is this patient going to survive or not? If yes, okay, how many days or how many months or years is going to spend before the eventual possible death? So the second stage is going to be the regression problem because you are predicting numbers directly. And then we have an example also in that. If you go here now, I'm going to load a different data. This time around, I think that was this was CPU, should be. Yeah, so this is classification model. So maybe I choose to use function. I want to use MLP. Okay. That's all right. No problem. Okay, sorry. We can see the error. So the error is given is that problem evaluating classifier. No user test set has been specified. This is the first thing. You know, I didn't specify anything here. So the data is not big. I rather say, okay, go for 10 cross validation, and then here you go. You can see total number of instance. You can see the output is different from what we used to have for classification. This because this is regression. See, it's giving me the actual prediction. The actual was 70. My machine learning predicted it to be 78. This is the error. This one 116. It predicted 142. This is the error. Sometimes you have negative error. And that's why you're going to, all this error will be summed up in a unique way, either using means absolute error, root mean square error, relative absolute error, root relative error, depending on the kind of application area. Each application area has a particular or specific means of evaluating the regression outcome. So the two popular one is the correlation coefficient. It's used mostly anywhere. This is a measure of how the prediction flows with the original values. Are they flow in the same way? You can see there's a flow. 0.88 is high. You can see 12, 10, 5 something, 5 something, 1 something. You can see they almost following the similar pattern or something closer. The root mean square error, we try to scare all this error in order to avoid the effect of negation. And then find the square root again. Mathematician will tell us they have not done anything. We only scare it and then we find the square root again. So nothing is added to the number, nothing is removed. So that's what we were taught. So that is regression problem, how we can use it also in our weakers. So now we move on. So having discussed that, we also mentioned something we call bias variance trade-off. So when you are developing machine learning application, these are issues we have to pay attention to. We come across it. So there are 3 major things that are sources of error in our machine learning models. The first one is known as the noise. We call it unavoidable error. It is the noise in your data. Your data is not very clean. Data is dirty. So you need to clean your data with soap and whatever you want to use. We talk about that under pre-processing. Then there is the bias, which is error due to incorrect assumptions. You make assumptions during the training of your model, then it leads to your model being biased. Then there is variance, error due to the variance of training samples. Depending on the kind of training samples you are using, then you can run into trouble getting good results. And that is why some people will advocate the use of cross-validation. That we want to see how every member of your data set is doing, is contributing to that particular model building. However, you cannot do that if your data is huge. You have 2 million, 3 million data, and you are going for cross-validation. That's a sheer waste of time and energy. So because it's going to take you a lot of time. Running those huge data 10 times or even 5 times will be very big. However, when the data is very few, what should come to your mind immediately? Try the cross-validation as a means to avoid the biasness of your data or otherwise, or variance. So we can play with this one depending on the power of our machine learning algorithm that we are using. Variance and bias, you can play with it. However, this guy, you cannot do anything with it. It comes with the data. That's why some people call it irreducible error. You cannot play with it to make it small or smaller or increase it. Rather, you might have to go to your data. It comes from the data. If the data is bad, then it will affect your result. If the data is very clean, very good, neat data, then it will also assist your result to be better. So in making these trade-offs, somebody needs to be very careful. You try to, because bias and variance, unfortunately, they are on the opposite side of the divide. When you are trying to reduce one, the other will be increasing. See? So this is an idea where you have, you can see here, you have low bias here, high variance. You can see they are opposite. Here is high bias, low variance. So if you go close here, you have low variance, but you have high bias. If you go too much here, you're going to have low bias, but high variance. So they are opposing themselves. So that means you have to have a middle course. We have to stop. See, you don't stop at this point. At this point, there's going to be high bias. which is not good for your model. At the same time, if you go too much far, there will be high variance. So we want something in between the two. You see, what is happening here is known as underfitting. Underfitting means high bias and low variance. It means both your training error in underfitting, both your training error, your training accuracy and your testing accuracy, they are both bad. Your model does not understand what you are trying to make it understand. So it's a bad place to stop training. That is underfitting. You see, and that's why you can see that the training error is high, the testing error is also high, even higher than the training error. But when you move further, you got to a point that the training error is almost going to zero, which is great. But then you don't celebrate. When your training error goes to zero, you need to check the testing error first. You can see at this point, our testing error is still reasonable. But because human beings, we are sometimes very greedy, we want always 100%. When you want to get 100%, you might get it at the expense of overfitting, which is going to be a trouble for you. So what happens is this, as you start going down until your training error goes to zero, then the testing error will start increasing again. At that point, we call it overfitting. Low bias, high variance. You see? So that is why when you report the training error as being 99% accuracy, you don't celebrate until you have gone back to check your testing error. The testing error is the one that would tell us if your model is doing fine or not. Because you could get actually 100% here, the training error, but then you can see here it's already up. You're getting 56% accuracy. This is overfitting. Overfitting means your model is performing excellently well on the training set, but when you give it a new set that it has never seen before, it's not performing. It's having a very bad result. And the aim of training a model or developing a model in machine learning is for you to be able to predict the unseen data. Our target is unseen data, not the one that we have seen before. See? So that is why the testing error is very, very important. So then what do? If we stay here, it's underfitting. If you go here, it's overfitting. And that is why we have to be in between. You see, as Muslims, we are ummah wasat. We always advise to be at the middle. So don't stay on the underfitting side and don't stay at the overfitting side. You have to stop somewhere in between the two. Okay, I just want to reduce the training error a little bit more. Well, it's good to reduce it more, but be careful that you don't run into overfitting. Because it's not this training error that is our problem. Our problem is the testing error. You get 100% here, you don't get good result here, we will reject your model. If that model is useless because it is overfitted model.
Yeah. Assalamu alaikum, doctor.
Walaikum salam.
Yeah, thank you very much. Yeah. You use the word unseen, the unseen data. So I would like to ask, if you want to test after training, then you want to test another set of data.
Yeah.
So is it possible that the output, what you want to predict, those values, can we remove them and give it to the model? To the model to predict.
Yeah. Well, this is what is happening in every system. Thank you for that question. This is what is happening in every model development. You see, the fact that we are supplying our training and testing set to weaker at the same time, it doesn't mean the model is seeing the output. Are you with me? It's a program that has been written to make life easy for us. You see? So yeah, it's a program that has been written to make life easy for us. So when you are like this, let me bring this up and use it to explain to us. Can we see my screen?
Yes.
Yeah. You see, when you say percentage split, use 82% for training. The remaining 18% are kept hidden from the model, actually, the way the program is written. You see? Because this is GUI. This is GUI. They have to collect the information from you and keep it somewhere. But the normal thing is that even though they have collected the unseen data from you, the model is not allowed to see it.
Okay.
That is clear, okay? So
Yeah, very clear.
exactly. So what they do, what the 82% for training is the one that your model is going to see. You give it
Okay.
you also give it the output. This is what Weka will do. And this is the standard for any machine learning platform. During the testing period, then that one is not seen. The output is not known. They only give it the input based on the training we have given to you. Now tell us the output of this new sample. And then it will do that. Either the first, if you divide your data into two, the second one is to be kept as hidden, unseen data. If you use three, the last two also will be the hidden data, I mean the unseen data. Both the validation set is not seen before, and also the final testing set. They are not seen before. Is clear, Doctor?
Yes, very clear. Thank you very much.
You're welcome. So that is on the bias. So we have to look for where to stop at the middle. So like we said, the unseen data is the data that is kept separated, waiting for the model to get trained. And after the training, we now give it to you. Okay, Mr. Ma, you have been trained. Now tell me what is going to be the classes of these new samples. Then it will try to predict it out and see. And sometimes, because some company, they were confused, they said, okay, but we sent the data to you, this testing set. We sent it to you. So maybe your model already seen it. We said, no, we didn't expose our model to it. We didn't use it for training. And that professor, there was a professor like that, professor of chemistry, he said, I already gave you the data, I don't believe. I'll give you new data now. Fresh. Said, okay, no problem. Yeah, this happen, because you need to have to get their trust. We said, okay, go ahead, give us new data from your laboratory. He said, and you have to bring your laptop to my office. You see the point?
He wants to be sure.
Yeah, they told the professor they got like 98% accuracy. He couldn't believe it. He said, is it possible? So the student went to his office with the laptop, and then he brought out new samples on the same data. And then they slotted it in and they predicted it. And since that time, that professor now is a fan of machine learning. He has always been using machine learning because initially he never thought it was possible. So he thought that was manipulation. So thinking that because he sent the data to us, we already exposed our machine learning to that data. So he said, you are getting good result because your model already know this data. So that is why once we deploy for the client, we also encourage the client to provide additional new data for testing. You see? So the more the testing you do, the more the confidence of the client that somebody can get. But when the data is very few, then you don't have option. You have to use the little that you have. Even cross-validation. In the cross-validation system, is still a proof of concept that this model, given the many, if you are able to get other data, it's likely going to work for us. Because if it's not going to work, even the cross-validation will not work. So this is the idea. So we have to know where to stop at the appropriate time. When you are doing bias variance trade-off, you go to the right too much, you're in trouble. You go to the left, that is underfitting. Now, finally here, under bias variance trade-off, you see many training error, you can see. If you have many training example, this is testing error. This is only testing error. There's no training here. This is testing error. This is the effect on testing error. The idea is that if you have many training example, your testing error is likely going to go down. This is why we recommend the more data is better. But when your data is very few, during the training set, training example is very few, most likely your testing error is going to go up because there's no magic in that. So the more data you expose the machine learning algorithm to, the more the possibility of getting good result. This is how you can also do a trade-off between bias and variance. And at the same time also, you can also see that there is too much of everything. Even if the data is too much at a point in time, you can see that the error also can rise, actually. The error can still rise. And that is why the ensemble model we want to talk about later, once data becomes so big, it might be better for you to split the data among different models and build models different model and let them vote and cooperate to get better results. Because even too much data sometimes can lead us finally to having high variance, which can be a source of problem for the system. But then the question is, how many example data is too big? That is a question that no one can answer. So we have to let the data speak. Always remember that principle. Let the data speak. So you bring your data, we plug it into the system, and then we see if it's going to work. If it works, that means the data is okay. If it's not working, then we might have to look for more data, or we might have to do other things to do it. So this is another effect on the training size example. So if the number of training example, if you can get as many training examples as you can, it is hoped that at least within reasonable limits, at a point in time, the training and the testing error, they can probably converge at a point in time, hopefully. If your training error example is normal, it's okay. It's the effective one. So this is when you fix your prediction model to a particular thing. So generalization is the difference between the training error and the testing error. What is the difference? That is called generalization. So that's why we look for the one that gives us the minimum. That is, the difference between the training and the testing error should not be much. During training, we are having like 20% error, but during testing, we are having 70% error. That's very bad. We want the difference between the two of them to be very, very small. So, but then when you are doing it, make sure you don't run into overfitting along the way. Otherwise, this one can go into 0 and then this guy will start going on. Now, so that is unbiased variance. And that's why we're going to stop for the day, inshallah. So remember, no classifier is inherently better than any other classifier. You need to make assumptions to generalize. So there's no classifier that is better. You have to let the data speak. So you have to make compromise here and there. So like they say there's no free lunch. So they say you can enter this building, you can eat food for free, but then you have to drop $10 to open the place. And when you enter, you want to eat $9 food. So nothing's really free. So in machine learning, the same thing. So we might have to make compromise, use as many algorithms as possible, and try to see which one is going to work for us. But to say a particular algorithm is the best, anybody that says that doesn't really understand how machine learning works. It depends on the data. I'd rather say, send me your data. And the principle of let the data speak has been the only thing that I see that is very stable in machine learning and data mining application. So you can use the same algorithm for one data from the same clinic. Tomorrow, the same clinic sends you another data, that algorithm is not working. This is it. So 3 kinds of major error: the unavoidable error, which is the noise, the variance, and then the bias, as we have explained. So we are going to stop at this point, inshallah. We start with the revision of preprocessing business line next week and what's related to it. Now,
I have a question. When do you know that you're in an overfitted area or underfitted area?
When do you?
Yeah. When, or just can you kind of guess them? Yeah.
Okay. You say, when do we know we have arrived at overfitting or underfitting? Yes. Yeah. Thank you very much, doctor. So what you do is, you see, there are a lot of, this is one of the biggest problem of neural network. Neural network it's the big father of machine learning. So it's the foremost method. One of the major problems of neural network is it suffer from overfitting. So people try to come up with a couple of different versions of neural network to try to beat that overfitting. The best way to, only way and the most reliable way or realistic way to know is you have to keep checking your training error. See, to check your training error.
Okay.
You see, if the training error, and that's why if you divide your data into 3, some people like to divide data into 3. We have the training set, we have the validation, and then we have the testing. If you have 3 or 2, any of the 2 is fine. So always check your training error. What is the training accuracy? My training accuracy is 99. The moment I start getting 99 for training accuracy, I'm afraid I need to quickly check for the testing error. What is testing accuracy? And I got 86. This is okay. We don't consider this overfitting. It's fine. Your training error is getting 99. This is 86. This is still fine. Something it has never seen before is getting 86% accuracy. But I got 99%, and then for testing, it gave me 30% accuracy. No, this is overfitting. This is unacceptably, the difference between this and this is too high. Or I'm doing my training, I got 87% accuracy in the training. Immediately you have to check the testing set. That is why we pay attention to the testing set. We don't stop until you have seen the result of the testing accuracy. If the testing accuracy is 86, oh, this is excellent. You keep training, you do more training, maybe you can get this one to be 99, and this guy can stop at 95. That would be excellent. If you can get such a thing, this is what we look for. So you have to be checking the result of when we are during the training, we can be using these two, train and validate, train and validate. So we'll be checking the validation result at that point in time. If it is okay, you keep going. Keep improving your training by changing the parameter, by changing the number of variables. We are going to discuss some of the ways we can improve our model performance. So once your validation checking is okay for you, then you know that we don't have overfitting. However, training and you get 100%, then you have to go and check your validation quickly. 100% in training is like your training error is 0. Once your training error is 0, any time from that, overfitting can take place. But always, actually. So to quickly go and check what's my testing error? Oh, my testing error is now 95. Oh, let me stop here now. Oh, let me do little more. It's 97. Oh, let me do more. The moment you start doing more, you find out that it dropped from 97 became 66% accuracy. That is an error. You know that, oh, I've run into overfitting. Let me go back to where I was before.
Okay.
That is clear, Doctor.
Yeah. It's clear. It's the gap between the training error and the testing error that I have to pay attention to, so I don't go under the whole thing.
Thank you very much. That is it. Barakallahu fikum. So another question? So that's where, inshallah, we are going to call it today here, inshallah. So this next week, we're going to continue with the pre-processing revision, what is involved and what we have to pay attention to, especially pre-processing as we are going to use it in our ensemble modeling that we are going to be introducing ourselves to Bismillah. Barakallahu fikum.